Okay, so today, this first video, we're just going to create a basic decision tree model. And then later in subsequent videos, we're going to experiment with bagging and boosting. But let's just get our first basic decision tree model going first. So I've gone ahead and done all of my imports here, but I'm going to list them for you just because I think this is kind of important. We can tend to kind of gloss over this. We can tend to kind of gloss over this as programmers, but actually these are our tools, and digging into these gives us kind of more mastery over what we're creating. So I'm going to bring in pandas, which is our data manipulation library. I'm going to bring in NumPy, which is our math library. And we're going to bring in PyPlot, which is a plotting library, and Seaborn, which is also a plotting library. And then from sklearn, which is our machine learning library, we're going to bring in the R2 score metric and the mean squared error metric. These are our ways to measure how much error our models have. We're going to bring in the label encoder, which helps us to translate strings and other things into numbers, which our model will need. We're going to bring in our from our model selection kit or whatever. We're going to bring in train test split, which is going to split out our training and testing sections of our data. We're going to bring in our cross-validation score, which is going to generate cross-validation for us. Repeated k-fold, which is going to do multiple folding for our splits. Our grid search, which is going to do the thing that discovers what the optimal parameters are for our model. And actually, it can discover which model is best. It does a search over all your different variables. And we're going to bring in our decision tree regressor. That's the actual model that we're going to use. And we're going to bring in a bagging regressor that we'll use later, and the XGBoost regressor, which we'll also use later. So those are our imports, and these are kind of give us the tool set that we're going to use for our model. So first thing we're going to do is get our data set ready. So I'm going to create some code here, and we are going to be using a data set of pricing data for house prices. So I'm going to call it house price data. And I'm going to bring it in with pandas. And I'm going to read a file on my local machine. And it's just called train.csv. And then I'm just going to get the head of that so we can see how it worked. So we have our data. It's kind of truncating the sides here. But, we got our basic features of our data: month sold, year sold, sale type, sale condition, sale price, what type of street it is, lot area, etc. So that's working. And we've got 81 columns. It's only showing 5 rows in the head. But the next thing we're going to do is get a little bit more information about our data. So we're going to do that by doing a describe. So this describe is telling us the metrics of our various features. So like, let's look at lot frontage, because that's the very first one that looks like a really relevant piece of data. There are only 1,201 lot frontage things, where it looks like there might be 1,460 rows total. I can actually figure that out by changing this to shape momentarily. I'm going to do a shape. Oops. No, that's not a method. It's just a parameter. Okay. Yeah, it's 1460 by 81. So then I'm going to go back. And I'll just leave that there. Why not? Then we'll do our describe. Yeah. So it's giving us the metrics. Lot frontage, only 1,201 have listings for that apparently. The average mean average is 70, not the nice average, the mean one. The standard deviation is 24. Our minimum is 21, or 25% of our quartile is 59. 50% quartile is 69. That might be kind of like our mode. Actually pretty close to the mean, so it's probably pretty much a bell curve or a Gaussian curve. 75% quartile is 80, and our max is 313. And then we have those for all of them. So first we're going to get our split set up, and then we're going to actually kind of munge our data and do our EDA, fix it up for ourselves. So this X variable is going to be our the data that we're actually going to the features that we're going to try to have the model crunch in order for it to then finally predict the sale price. So for that data, I'm going to get some data from our house price data, but I'm not going to include two pieces of information. I'm not going to include the ID because that looks to be random, and I'm not going to include the sale price, or it's just an index, not random maybe, but it's an index that's not relevant to us. I'm not going to include the sale price because that's the thing we're actually trying to predict. And then I'm going to do axis 1, and that's going to give us the columns rather than going vertically down the rows. Then our y variable is going to be, we're going to get just the sale price. So this y is going to contain the values that we're targeting, and so we can test against those. And the x is containing everything else. So then I'm going to set up our train test split, and when that throws results, it's going to give us x train, x test, y train, and y test as outputs. So we're going to do a train test split, x, y, and we're going to do our test size as 0.2. That's going to give us 20% of the data as our testing data. We're going to do a random state of 1, and that's just going to keep it from giving us varied outputs every time we run it. So I'm going to run that. It appears to have run without an error, so that doesn't give us an output except for these values. So we could just say, what's x train? Oops, misspelled that. Get the head of that, the EHAD, the head. Okay, so it's there. There's x train, x test is going to be the other 20% of the data. We could do y train. Okay, that's just that one column. Those are the sale prices. And y test would be the same thing. Okay. So now in our data, if we actually go back here and look at x train head, we can see that some of these pieces of data are numbers, but some of them are strings and nons. They're basically no data. And so we need to clean those things up. So the first thing is we're going to clean up these nons. So we're going to convert these just to 0 so that our algorithm doesn't choke on them. So to deal with the non-values, we're just going to fill our data with zeros wherever that non exists. So we're going to do fill NA, which is a special function that does that for us. We're going to pass it 0. That's what it's going to put in there instead of that NaN. We're going to say in place equals true so that it doesn't throw us a different data frame. It's just going to replace the existing one. I'm going to do the exact same thing for this one. Okay. And then when we run the head on that, now we can see here, instead of NaN for Ali, we get 0. And it's going to be the same anywhere else. We have NaN, so pool QC 0 instead of NaN. Cool. And then our machine learning model also really can't deal with strings. It really can only deal with numbers. And so we're going to replace the strings with numbers using the encoder, the label encoder. So the first thing I'm going to do is instantiate the encoder. And that's just a label encoder object. Okay. And then we're going to run through our columns, and every time it gets something that's not a number, it's going to convert it into a number. And those are going to be categorical representations of those strings. So I'm going to run a for loop, and I'm going to call my iterator column in x train. I'm just going to do that one first. And this time I'm going to exclude anything that is a number, because we want to leave those alone. And then I'm going to run the fit transform with my encoder. And this is going to go through and actually, figure it out, basically figure out what needs to change. So we're going to run it on X train, and we're going to run it on each of our iterated columns. Oops, column with an N. And then we're going to convert it to a list at the end, just so that the next step can actually ingest that properly. And then we're going to replace our existing data with what we just got from that thing. So I'm going to go to that same column of our existing data, and I'm going to replace it with the encoder data. Encoder.transform x underscore train in that same column or data. So this is going to say, take what we encoded from this one column and then replace this original column with that data. Okay. So let's do that and check it out to make sure it's working. I'm going to do xtrain.head again. Got an error. Data frame object is not callable. Oh, I'm not doing my select. Select D types. Boom. Okay, that worked. All right, so what was text up here, LVL, is now a number, and these numbers are it's going to have created categories for each one of the various text items in there and assign a number to that category, so that then our algorithm can actually deal with those numbers. But we also have to do this on our testing set. So I'm going to get rid of that guy, and I'm going to copy this guy. And I'm going to do the same, but for the test set. So I'm going to use multi-cursor here. Just select all of these spots. You go beep, 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 and beep, beep, beep. Okay, so now we got the test one. So let's make sure that that's working. I like to do lots of traces, console logs, if you will, just to see that every step that I do is working before I move on, so I don't get confused. So yeah, our X test also has the numbers. Boom, our encoder worked. All right. So now we're ready to actually train our model. So let's make a model here. Our model is going to be a decision tree regressor. And we're going to assign it a random state like we do every time we get a chance, so that we don't get random stuff. I wish that could just be a persistent setting. We're going to then create a list of parameters that we're going to send to our test grid to run to see which ones perform the best. So we got two parameters for this regression tree model. We got max depth, and then we're going to just pass an array. I'm going to do 2, 4, 8, 12, 16, 24, and 32. This looks like a Fibonacci sequence, kind of. Not quite. Okay, and then we're going to do max features. And that one, I'm going to do 0.1. I'm going to do every percentage. Now these are going to give it percentages. So it's how many of, what percentage of the features are you going to do? So I'm going to give it every 10%. And 0.99, because I think it'll interpret one as just one feature. And then I'm going to also give it the square root of the number of features just for fun, and log 2 of the features. Just for so little variety there. Let's get some variety in there. Okay, and then we're going to do our search. We're going to set up our search. It's going to be the grid search CV. Don't ask me why it's called CV. Maybe it's because of the folding part of it. Model. We're going to pass it to the model. We're going to pass our DT parameters. And we're going to do 5 folds. That's the CV parameter. And then our scoring is going to be R2 scoring, R2D2, not to be confused with. And then we're going to run our fit, which is kind of actually, basically running the algorithm, running this grid search to figure out which one of these sets of parameters is going to work best. That's not, we don't want the F train, not in New York City. We want the Y train. Catch the Y train. Yeah, so I'm going to run this now and see if it works. Oh, got an error. DT fits. No, I didn't do that right. This is DC search dot fit. Okay. Do your thing, mighty engine. Okay, this means it worked. It gives us this little blocky thing here. It doesn't really say anything except what we put into it, but it didn't give us an error. So it actually did the decision tree. And now we got to see what it said. What are these settings that it came up with? So I'm going to figure out, I'm going to ask it, what's our best model? DT search dot best estimator. Okay. Our best parameters. DT search dot best params. And then our prediction. So we're going to get a score out of this prediction. And we're going to run it on the best model. Best model. We're going to run a predict on it. And then we're going to run it on the X test set. So how well does it do? We're actually going to run the model that this thing came up with the parameters for, and then we're going to be able to see what its error rate is. So let's find out what those parameters were. And let's find out the score of our test. Let's see. of the best stuff. So we're going to run R2 score, prediction, and Y test. So how well did that do? And then let's find the mean squared error just for fun. Okay. Okay, let's run this, see if it works. All right, cool. So our best parameters were 8 and 80%. So it went 8 levels deep with our tree building. That's interesting because it works best when it doesn't go so deep. Isn't that interesting? And then 80% of the features was the sweet spot in terms of how many features to use. And it went through and figured out which ones were performing best and used those 80%. And our R2 score is 79 out of 100, which doesn't seem too bad to me. And the MSE, we can't really interpret that because we don't have other ones to compare it to, but there it is. So what we've done today is we've gotten set up so that we can actually implement a basic machine learning model, this decision tree regressor. And we've gotten set up so that we can clean up our data with a label encoder and our thing that cleans up the non-values. We've gotten set up so that we can do our testing on it and get scores out of it. We've got our basic tools here. And then we got our tools to actually figure out what the best parameters are, use the computer to figure that out. And then we went ahead and imported our data. We took a look at it so we could get an understanding for the data. We created our splits. Then we cleaned up our splits, removing the non-values. We cleaned up the strings by turning them into numbers for categories. Then we actually did our training of our decision tree model. And then we checked out the results. We could see how it scores. How does it do? Later on, we'll keep going further, and then we'll get into the bagging and boosting so that we can further refine the model. See you next time.